In this video, we're doing our part 2 of solving this problem where a stone is thrown upward on another planet. And we've already calculated the average velocity between 1 and 3 seconds by just plugging into the original function. Average velocity meant slope. Then we figured out when the stone will hit the surface. And lastly, we're going to figure out with what velocity will the stone hit the surface. This is the most challenging part because to find the velocity at a specific instance, we're going to need to take the derivative using the 4-step process, plugging into the limit definition. So I've copied this original function down here so we can see it below, and we're going to plug in to the limit definition of a derivative to calculate this velocity at the specific instant. So our limit definition is typically the limit as h goes to 0 of f of x plus h minus f of x all over h. Of course, we're going to switch out those x's for t's in this case. So we're going to plug into the first part, which is typically to just compute this f of x plus h here. So our first step, we're going to do h of really t plus lowercase h. So some different letters computing, and we're going to replace all the t's in the original function with t plus h's. So we have 12 t plus h minus 2.56, and we're going to do t plus h all squared. We're going to distribute this 12 in here to both terms. So we'll have 12t plus 12h. We're going to need to distribute that 2.56 as well, but we need to first figure out what is t plus h squared. If you don't know the perfect square trinomial formula, you're just going to have to do some side work and do t plus h times t plus h, right? 5 squared is 5 times 5, so t plus h squared is going to be t plus h times t plus h. So you have minus 2.56, and when you FOIL or distribute that all out, t times t gives you t squared. The outer terms end up being t times h, and then the inner term is also t times h, so you get 2th. And lastly, h times h is h squared. So we're going to go in and distribute this 2.56 to all three terms. So we have that 12t plus 12h minus 2.56t squared. And then we need to do negative 2.56 times 2, which is going to give us negative 5.12 th. And lastly, we have a minus 2.56 h squared. So we just computed our t plus h in there instead of x plus h, like typically how it looks with an f of x function. Our second step to plugging into that entire definition below is to subtract the original function. So we're going to minus out the original h of t. So over here, I'm going to do my second step, which is going to be to subtract all terms in that original function. So that's going to change the sign of both terms, right? We're going to have a minus out front of both terms, which is going to mean we're going to have a minus 12t. And subtracting a negative 2.56t squared means we're going to have a plus 2.56t squared. So subtracting both terms of the original function is our second step to plugging into that limit definition. And then we see a few things cancel out. So we have 12t and a minus 12t. And then we have negative 2.56t squared with a positive 2.56t squared. So what we end up with left after we subtract is a 12h minus 5.12th minus 2.56h squared. And we're getting closer to plugging into this whole definition. Our third step is going to be to divide by h. So we're going to take this and divide by h here, which means we can really factor out an h. So we would have h times 12 minus 5.12t minus 5.2 or 2.56h all over h. That way we can cancel out the h. So we did our first three steps. We computed h of t plus h. We subtracted the original function, change the sign of both terms. And then we divided by h. Our last step is going to be to take the limit of what we found. And this is going to give us our whole derivative of this position function, h of t. So we're going to let h go to 0 in 12 minus 5.12t minus 2.56h. So we let h go to 0 and we plug into our first piece, 12. 12 is going to stay 12. When we plug into our second piece, minus 5.12t, there's no h there, so that's going to stay minus 5.12t. And then lastly, we have minus 2.56 times h. This piece is going to go to 0. So our derivative, h prime of t, or also called the velocity function, is 12 minus 5.12t. This measures the instantaneous velocity for any time that we want to plug in. But it says, with what velocity will the stone hit the surface? So I'm going to replace that t with what we found in the last video. We're going to do h prime of 4.6875. Plugging in to that original, or that derivative, to tell how fast, and this is 5.12. 12 minus 5.12 times, we have 4.6875 seconds is when we hit the ground, or hit the surface of this planet. So our velocity ends up being negative 12, and our units on that are going to be meters per second, which that solution makes sense because we should be going down when we hit the surface. So we were going down by 12 meters per second when we finally hit the surface with that stone.